Hello there. So this is video number 2 of section 4.1. So we're just going to keep on looking at vector spaces in this section. Specifically, I want to start actually with the following example because I think it'll be a nice motivating example that will allow us to sort of transition into the main topic of this lecture. So if you have sort of those 10 properties of vector spaces that we've looked at and talked about last video, have those out next to you while you're watching this because we will be referencing those 10 properties quite a bit. And I just want to start out, we've got another vector space. So this is a set S of all vectors of the form T0. And so we're here, basically it's just all vectors of length 2 that have a any real numbered entry in the first entry. So 1, 2, you could have, pi 0, you could have 1.2520, even 0, 0. So here t is just a real number. So we'll specify that t is just any real number. And then the second entry must be 0. So basically, maybe a better way of describing the set would be to say S is the set of all vectors with a real number entry in the first entry and whose second entry is always 0. So we want to show that this is in fact a vector space. But I don't really like checking 10 principles every single time I have to show something as a vector space. And so here, I'm going to try and argue that we actually don't need to verify all 10 things about this vector space. And so why is that? Well, so notice that because these are already vectors in R2, we know that R2 itself is a vector space. And so a lot of the properties that are sort of just inherently true about vectors are sort of going to carry over from R2. So specifically, if we want to show that this is a vector space, properties 2, 3, and 7 through 10 follow immediately from the fact that R2 is a vector space. And that's because, well, we're going to define vector addition and scalar multiplication in this space exactly how we've been defining it with these with the sort of vectors we've looked at the whole semester. And so remember, properties 2 and 3 deal with sort of these not necessarily containment questions, right? So we can't assume property 1 because we'll have to show that a sum of 2 of these vectors, again, still is an S, right? So we don't immediately get that S is closed under addition. But property 2 is the commutative property. And since all of these vectors are just vectors in R2, well, they're always still going to be commutative. Same with property 3, right, which is the associative property of addition. Because that's true of just any vector in R2 anyways, that's going to be true about all of these vectors in S. And so if you think about it, we only need to check the conditions here. So that would be 1, 4, 5, and 6. That would be, I guess, specific to S. So that deal with either some combination of vectors being contained in S or a specific vector being contained in S, right? So we need to show closure under scalar. We need to show closure under vector addition, closure under scalar multiplication, and then we need to show that the 0 vector and that the additive identity is contained in S. So it's not quite as much work for us. And so we'll do that now. So we only have to check properties 1, 4, 5, and 6. And so to do that, we're going to just sort of let v1 and v2 be two arbitrary vectors in this space. And this is sort of generally how you'll want to verify things, is by, again, sort of picking vectors in a way that is as arbitrary as possible. So notice by picking t1 and t2 as the entries here, I'm allowing these vectors to be anything. And so I think one of the easiest things to do when showing something as a vector space is check like a specific example and say, well, the example holds, therefore, this is a vector space, but sometimes examples can be a little deceiving. All right, so first thing we need to check, since I've got two arbitrary vectors in this space, I want to verify that the sum of these two vectors is, again, a vector in this space. So by the properties of vector addition, this is the vector v1 plus v2. And remember, the defining quality of a vector in the space was 0 in the second entry, anything in the first entry. And so in this case, we can check property 1 off of the list. Number 4. So number 4, we need to check that the 0 vector is contained in this space. Well, I'm just going to let t1 equal 0. Well, if I do that, then this vector v1, which I've defined, is just the 0 vector. And so sure enough, this vector is contained in this space. All right, next thing, I'm going to let c just be any real valued scalar. So this is, let c be a real number. I'll say be a scalar. Well, I need to check that c times v2, and here I'll use the vector v2 just for the fun of it. Well, this is equal to c times t2, 0, and I can distribute c through this vector to get the following. Well, again, the vector I get here follows the rules of being contained in this set S, right? I've got a 0 in the second entry because c times 0 is always 0. I don't care what's in the first entry, and we're good. So, something really interesting. Actually, I only needed to check 1, 4, and 5, and I'll show you why. So, in fact, we're going to check 6, but I'm going to show that 5 will actually always imply 6. Right? So remember, 6 shows us that, or 6, the property 6, excuse me, is that basically, right, the additive identity or the negative of a vector should always be contained in the space. But once we've shown, and you'll prove this fact actually on your in your exercises, that basically the negative of a vector is just always negative 1 times the vector, which is one of those things that I probably would have just assumed to be true even if anyways. But anyways, once we've shown 5, well, by 5, negative 1 times v2, which is just equal to the vector negative v2, is contained in S. And so the reason being is that negative 1 is just a scalar, right? And we've already shown for any scalar, this scalar times v2 is contained in S. And so specifically, if I let this scalar be negative 1, well, then the negative of any vector is contained in my vector space. And so we've got 6 checked off the list. So we've actually reduced the number of cases we need to check from 4 to 3. That is, if I have a subset of a vector space, I only have to check 1, 4, and 5. That is closed under addition, contains the 0 vector, and closed under scalar multiplication. So, checking these 3, technically 4 things, we've shown that S is in fact a vector space, because remember it inherits the other properties from R. But we actually have a special name for S, because notice that S itself is a vector space, right, as we've shown, that is contained in a larger vector space R2. And so if this is the case, if we have basically larger vector space R2 and some smaller vector space S that's sort of contained entirely in this larger vector space, we call S a subspace of that vector space. And so we say that a subspace S of a vector space V is any subset of V with the following 3 properties. And so we've already seen an example of what these properties we need to check are. Well, it should be closed under addition, right? So that is for any vectors u and v in S, the sum u plus v is in S. 2, the 0 vector in V is contained in S. And 3, for any vector u in S and scalar C, well, C times u is in S. So that is closed under addition, 0 vector contained in S, and scalar closed under scalar multiplication. And so not only we get sort of 2 nice things about S, we get that S is a subspace of V, but notice this implies that S itself is a self-contained vector space. So this not only shows that S is a subspace of V, but it's a self-contained, S itself is a vector space. We will be studying subspaces quite a bit in this chapter and moving forward. Because really when we're talking about vector spaces, I think determining whether or not something is a subspace is the way more fun, way more interesting problem that sort of arises, because you can get really, really clever with sort of how you define it. So anyways, I actually just want to show you one more example of how we might show something is not a subspace. Then I would encourage you to try all of the attached problems where you can sort of work through these same steps in order to show that something either is or isn't a subspace. And so we've already seen an example of how to show something is a subspace. And so I just want to end with showing something is not a subspace. So if we show that something is a subspace, right, we have to, as generally as possible, or in the most general way possible, show that all of the 3 properties, which of course I just erased, are satisfied. In order to show something is not a subspace, we have to basically just find some counterexample. So find a set of vectors or a pair of vectors, a vector and a scalar that breaks one of the rules. So I'll show you how to do it. So we're going to let H be the following subset of R2. So it's going to be all vectors x, y of the form x greater than or equal to 0, y greater than or equal to 0. So this is the set of all vectors where both entries are non-negative. And we want to show that H is not a subspace of R2. So we want to show that H is not a subspace of R2. So whenever I'm given something like this, what I always like to do is start to write out sort of the most fundamental vectors I can think of in the space. So what do some of these vectors look like? Well, right off the bat, I know that the 0 vector is contained here. I know, like, maybe 1, 1 is contained, 2, 2 is contained. And so they kind of look like that. They don't necessarily have to be equal, so you might have, 3, 7, something like that. And why I like to do this is writing these vectors out, I kind of start to get an idea for, well, if I am going to show this isn't a subspace, how am I going to do it? So I've already shown that the 0 vector is contained in the space. So I can't use that rule to sort of break this idea. Well, I know that a sum of 2 of these vectors is still going to leave me with 2 positive entries. But notice, this space should be closed under scalar multiplication for any scalar C. And so if I want to break this, I'm just going to let C equal -2. Well, then -2 times vector 1, 1, where notice here, this is a vector V in my subspace H, right? And this is a scalar C. So what I've done is I've taken a vector in my subspace that I can show is in the subspace. I've taken any real numbered scalar C, and this product, this product is not in H, right? Because this contains 2 negative numbers. And so notice H is not closed under scalar multiplication. And so for this reason here, multiplication, for this reason here, H is not a subspace of R2. All right. So that will wrap up this video. We'll look at a couple more examples in the next video, and then we will move on to section 4.2.